And we're going to continue with this whole cell potential thing, but we're going to add to it. Yay.
Yay.
It's always fun. So what we're going to talk about is cell potential, which is what we've been working on. And then we're going to add to this electrical work. And then we're going to figure out how free energy fits into all this. And what symbol, what's free energy?
G.
G. So we're going to look at all those things. Now, a few things. Okay, we talked about this yesterday, but I really didn't define it because I wanted to get into what E cell was and that type of stuff. So we said that there's this EMF, which is called electromotive force. This electromotive force or potential difference both go by the same name of voltage. Okay, so you read a lot of different textbooks, you'll see EMF, you'll see potential difference, or voltage. They all mean the same thing. All of them are basically how much push you have on what?
Electrons.
Electrons, because you got push electrons. So the bigger the voltage,
Bigger the push.
the bigger the push. Okay? So that's what we're looking at here. And so if you remember from physics, what's work?
The amount of
Force.
needed to do
The
work.
amount of force needed to go a distance,
Distance.
right? Okay, well, don't we have to move electrons a distance
Yes.
by applying a
Electrical
force? Okay, so this whole idea of EMF, what it is, it's the amount of work that it takes to move charge. Okay? So it's the amount of work it takes to move charge. Okay? So work, thank you. What's the unit of work?
Joules.
Okay, so unit of work is a joule. Now, any ideas what a unit of charge is?
Cool.
Ah, it is a coulomb.
Coulomb.
Isn't it just a capital C?
Yeah.
Yes, it is a capital C. Man, you guys remember.
I just read the book.
Oh, okay.
Class.
Okay, so this equation then is usually shortened to, I'm just going to erase this, E equals work divided by charge. So the letter Q is charge. Okay, so W is work, Q is charge. Okay, and if we go back and look at the units of this, this is going to be a joule per coulomb, and that joule per coulomb is actually a volt. So a volt is a joule per coulomb. So a 1.5 volt battery means you have 1.5 joules per coulomb. That's what a 1.5 volt battery is. So this is really voltage.
Yeah,
Okay?
when you say per coulomb, like what is that? Is that like per electron? What?
Oh, 6.24 times. Okay.
Great question. Okay, because what exactly is a coulomb? So that's how we measure an amount of charge.
That's a lot.
So 1 coulomb is a lot of electrons, isn't it?
Yeah.
Why does it have to pick that?
Because that's mathematically how it came out.
Remember who made the rules?
Okay, so 1 coulomb is 6.24 times 10 to the 18th electrons. Don't confuse that with Avogadro's number, which is Avogadro's number.
What's that
Okay,
word again?
That's
1
given
mole.
to us on our That's 1 molecule.
Okay, so I just put this up here then, just to kind of get an idea of what a volt is. If you have 1 volt, that's equal to 1 joule of work done when 1 coulomb of electron is transferred between 2 points, whatever those 2 points are. Okay, and when we're transferring one coulomb of charge, we're really transferring 6.24 times 10 to the 18th electrons. So you just got to think of coulombs as a way to count a lot of electrons. If you have 2 coulombs of charge, you have
A lot of electrons.
2 times that, right?
Yeah.
Okay, if you have 3 coulombs of charge, you have 3 times that number. Okay, just remember a coulomb is a way to count a lot of charge. So now, what we're going to do is we're going to take this equation that we had earlier, and we're going to solve it for work. Okay, so multiplying both sides by Q gives you an equation for work. Work equals charge times,
QE.
and what's E?
EMF.
E is voltage, right, or EMF, okay? So now, how do you find out how much charge you have? Charge is calculated the following way. Okay, the way we calculate charge is equal to Q, which is charge, equals NF. Great. N is moles.
Of course.
Okay, it's the number of moles of electrons. Okay, and so that actually goes back to like nRT, right? PV equals nRT. Now, how do I get the number of moles of, that's the number of moles of electrons transferred. Okay, how do you find out how many moles of electrons are transferred? You actually go back to the half reactions. So if I just take a simple half reaction of zinc going to Zn2 plus 2 electrons, how many moles of electrons are transferred? 2. Okay? Because there are 2 right there. If I go Ag goes to Ag plus 1 electron, how many moles of electrons are transferred? 1. So that's how you find out how many moles are transferred. It's whatever is in the half reaction.
So you're only solving work for one half reaction, or?
Yeah, well, because what do we do with all of our half reactions?
Atoms together.
Yeah, and so the number of moles transferred in both is the same anyway, right?
But you wouldn't have it, 'cause they cancel out.
Yeah, they cancel out.
Oh, but we need it, well, we need to find out how many are being transferred though.
At first, initially.
Yes, because they are being transferred from one thing to
So
another.
technically, if those were the 2 things that you're reacting, you would just put 2 because you have to multiply that by 2.
Yeah. Correct. Okay, now, F is a constant. It's called Faraday's constant. Okay, and Faraday's constant is 96,485 coulombs per mole of electrons. Now, on your AP Chem equation sheet and in various resources, they round this number. Okay? So this number is oftentimes written as 96.5. Okay, coulombs per mole of electrons.
Which one would you say we should
Use the one on the AP Chem equation sheet, and I don't know which one that is.
This one says 1 electron volt per atom.
Yeah, we're not doing electron volts yet.
96.5 kilojoules per mole.
Where are you at?
Where is
Yeah.
I don't know where it
No,
is.
that's electron volt per atom. That's all right. Faraday's constant, 96,500.
It's on the bottom of the last page. It's the very last thing on the bottom of the last page.
96,000.
Oh, that's what that funky is.
Right. Oh, so we should point that out. Their F is different than mine, right? Look on the AP
It's a
Chem.
script F.
Okay, so that's Faraday's constant. Okay, so then, okay, what you have to realize then is what I'm trying to calculate here, okay? I'm back to trying to calculate work, right?
Right.
So if you think about this work, the work that's done is equal to the number of moles of electrons moving times the voltage it takes to push them. Does that make sense for work?
Yeah.
How much work I'm going to do is how much push I have on how many electrons I'm going to push. Because really, this term right here is really figuring out how many electrons you have. Okay, that's what the NF is. So it's the number of moles of electrons moving times the voltage to push them. So this equation then for work, instead of putting Q here, because this is work equals Q times voltage, we're going to put the NF in there. Okay, so work equals NFE. Okay, now, one minor detail. We're going to add a negative sign in front of that.
Why?
I love the collective why.
Are you going to show us the math?
No, I'm going to tell you. The reason why is to follow our sign conventions that we've been using for going from a system to surroundings. Okay, and in this case, though, it's negative because the work is done from the system to the surroundings, and when the system does work on the surroundings, that's been negative. So it's just to follow our sign convention.
What happens if you have it the other way around?
Well, then it would be positive work, wouldn't it?
But you still leave the negative sign in there?
Yeah, we are always going to do this because the signs will work out.
Even if the surroundings do the work on the system?
We're not going to worry about that.
Okay.
So now, because it's going to come out here in a second anyway, your question is going to be clear as mud in a minute.
So not.
So this equation then is the net work done by the transfer of electrons available to do useful work.
And it makes any sense. Yeah. Is net work done by transferring to
This equation is the net work done by the transfer of electrons that is available to do useful work. Well, the whole point here is what's useful work?
We don't know.
That's how much you paid.
No, you do know. You do know. What's useful work? What's useful work?
Useful work is work that is
Work
useful.
that is useful.
Free energy.
Free energy.
I was going to say that.
Useful work is free energy from the last chapter. The energy, the net energy available from a reaction to do useful work is free energy. So this equation is going to change yet again.
So when did we stop?
Delta G.
So delta G is actually work.
Delta G.
So then delta G equals this minus NFE, and the E is actually E0.
That was a third way to find out.
Yes, so this is yet another method to find delta G.
Oh, man.
Now, delta G, to go back to your question, Bree, can be positive or negative, right?
Right.
So it's going to
Makes
come
sense.
out right here.
So you could find work with like delta H, delta S, and
Yeah.
So,
Oh,
so you can find if it's like spontaneous or
E.
not.
Makes sense now.
Right. So this equation right here, okay, is the calculation of free energy under standard conditions. And our standard conditions for this is what?
One
ATM.
One
SCP.
0 Kelvin.
Which is
Zero.
no.
These are solutions, which means it's 1 molar, right?
Yeah.
Okay. So here's an example.
Well, I didn't
Wait, I
didn't write that second part
calculate
either.
Calculate brand under SCP. Okay, that's all we need.
I'm not.
Just write under SCP.
So here's what we're going to do. We're going to take this standard half cell reaction. And the first thing you want to do is find the cell potential, which is what?
The electrons transfer? No.
This is what we did yesterday.
It's in one.
So this is to take the two half reactions that I've got going on here. So I've got Cu yields Cu 2 plus plus 2 electrons, correct?
Yep.
And then Ce4 plus is going to Ce3 plus. How does it do that?
It adds an electron on the left.
So it gains an electron. So there's my oxidation reduction. So I need to find the E of the oxidation, and I need to find the E of the reduction. So you're looking for those. You look them up.
Negative.
So it's negative.
Why are you negative?
See you.
No, you can't do this.
Where's CE?
You have to flip it.
Yeah, but it's not negative.
CE is 1.6.
0.15.
Or negative. No, you did it
Oh,
wrong.
how's CE on here?
CE is
Oh,
1.7.
we're gonna use our book?
So it's
Oh, yeah,
negative.
use your book. That's one.
CE.
Wait a sec. CE.
Where's CE at?
It's in your book.
CE is 0.17.
CU.
What's CU?
0.34, but you have to
Negative
take
0.34.
It'll be
Ah,
negative 0.34.
there we go. So it's minus 0.34. So I really don't care about actually adding the reaction together, do I?
No.
No, you can if it makes you happy, but you don't have to. All I care about is what is the E of E0 of the cell?
Negative 0.17.
What?
What?
Yeah.
1.36.
1.36.
It's 1.36.
Oh, it's 1.7, not 0.17.
Sillies. Sillies.
So, the E of a cell is 1.36. When? Standard
Standard
condition.
condition.
Okay, so now if I want to find delta G under standard conditions, delta G is N F E0, right?
Isn't it negative?
Thank you. Okay, so now, what is N?
Well, and what?
One.
Negative 2. 2.
Two.
No, it's 2.
No, wait,
No, it's
what?
not. It's 2.
Which
one?
one?
Which
one do
It's
you
2,
do?
because you have to multiply the second one.
They cancel, so it's one.
It's
No, it's 2 because you still have to get it equal and then they cancel.
You have to get it equal, so it has
Yeah.
to be 2.
Thank you.
N has to be 2. So, because you do need to go and multiply that by 2, because you can't do these without that. So, N is 2. What's F?
96,500.
96.5.
Oh yeah, it's a constant. I was like, I don't know. Well, how do you get that?
It's a constant. And then E cell is 1.36. So
Are you
this
supposed to round it?
this becomes plug and chug.
Do you have to round it?
Negative
2.
262.48. Isn't it negative? Crap.
I keep forgetting that negative.
Equals a lot.
Is it joules per mole?
What did you get?
Good question.
Negative
It's joules.
262.48.
This is going to come out in joules. I'm sorry.
Yeah, I was gonna say, that's a lot of
Why is it
kilojoules.
negative? And when it's positive, it's negative. You forgot to put negative in
What is it? Negative 26.
262.
Negative 262.48.
Okay. Now, yeah, I should have put units in here.
Question.
Yeah, why?
Okay. So the N is moles, right?
Yeah.
So this is moles of electrons times a coulomb per mole of electrons, right? Times a joule per coulomb, because that's what voltage
So
is,
it's
right?
joules.
So moles cancel, coulombs cancel, you're left with joules.
You want us
How
to
can
change
G
it to
be in
kilojoules?
joules or?
You should always put it in kilojoules. What?
How can G be labeled as joules, but it can also be labeled as joules per mole? Like with the heat and the.
Because that's just heat. That's our energy from before.
Should be the same.
So delta G is minus 262.5 kilojoules, correct?
Yeah.
Now, is that spontaneous or non-spontaneous?
Spontaneous. Non-spontaneous.
No, it's spontaneous.
Spontaneous.
Okay? So now, to answer Bree's question from 10 minutes ago, okay, how am I going to know if this comes out, could this ever come out positive?
Yeah.
When?
When you have
When
negative.
E is negative. So, and that would make sense then, right? Because a negative E means you're non-spontaneous, right?
It makes it positive.
So then putting a negative E in here makes it positive, which means delta G will be non-spontaneous. See how all that just mushes together? And it's still as clear as mud. Okay,
Okay, we're getting a little better than mud, so can you like say something else? Clear as
Milk.
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 There we go. That's a little better.
okay, so let's muddy the waters again then. So what if the concentration in this same equation, I'll give you a chance to write it down because people like to write.
I remember in 8th grade calc, I didn't write anything, and it was fine. Now to write everything in here, then it's not fine. That makes sense.
Yeah, I am recording this, just so you know.
That's okay.
So, what is the concentration of the, or if the concentration of CE4 plus increases, what happens?
Then the G increases.
The electron. Oh, never
No.
mind. I don't know.
C plus 2, 2C plus 2 report down.
Left or right?
It'd be-
I'm saying this increases.
It's gonna go left.
It's gonna shift to the right.
To the
Right.
right.
Shift
Right.
That's the down, because the other one goes
Yeah.
up.
This is the stress.
That's right.
It's gonna have to go down. The other side's
That's
gonna
go
go
down.
down.
Right.
It's gonna have to go up.
So it's gonna go to the right, yep. guys
There
are-
you
So
go.
it will be product.
Ah, but now, what does that do to the voltage?
It increases.
It increases the voltage. So changing these concentrations changes voltage. Yay. So this reaction is going to shift to the right, increasing the driving force on the electron. Therefore, the cell potential will increase.
We need to stick to one word. Self-control, EMF,
Voltage.
voltage.
If we stick to V,
Are we done?
Oh, no, 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 no. I'm just giving people a chance to write, even though apparently writing is futile. So the whole idea here then is that changing concentration is going to affect cell potential, which means ultimately we need a new way to get cell potential, don't we? Yes, we do. Yes.
How can I reach?
Can I go this high?
Yeah. What are we doing?
I'm just waiting for people to write. Okay? So here's the effect then. Okay? I'm going to change this. So when concentrations change,
Isn't this how our original one?
yeah, delta G is going to change. And when delta G changes, from the last chapter, this was the equation that we had when delta G changed. And so we should still be able to use this equation.
Why this one though?
Because guess what delta G equals? Minus NFE, right? So guess what we're going to do here?
is that delta G without
Combine
zero or
them.
with the zero?
With zeros. I guess I didn't know I had it
Negative
written.
NFE equals plus.
So we are going to substitute all of those in. So this is going to get substituted in there. So minus
Why would you
Why is it
NFE.
The other one.
Julie,
You
it's
have a
all
zero.
Do zero.
You have
the
the
G.
cell
I know.
phone there.
Just hang with me.
Oh, good to know.
Okay, we're going to put them both places because this is under standard conditions, which is what this means, right? This is delta G under the new conditions, but under the new conditions, you're still going to have a voltage. So it's minus NFE will be then plus RT natural log Q.
Oh my gosh. We need a note card.
Okay? You have a note card.
No, we don't. That was physics. We had like 500 note cards.
We're going to divide each one of
Wait,
these.
I'm even
Okay? And we're going to divide these by minus NF.
That's it.
So I'm going to divide this by minus NF. So I'm going to divide this by minus NF.
E equals
So E equals
E0.
E sub
E0
Plus
plus
RT natural log Q over negative NF.
RTF
got L and Q.
and LNQ.
Negative
Would
NF.
be-
Wait, so you
negative
divide
NF.
RT by
And-
NF before you times it?
And it is now negative. Thank you.
Julie. Divide L and Q.
Okay, just a second. Yep. Now, but mathematically speaking, I can pull this out in front. That's what I'm doing. I can pull this term out in front of the entire thing. It's the same math. So that's what I'm doing. But I'm even going to take this one step further. And what's R?
0.0081314.
Okay, except we're going to do it in joules this time. So it's 8.31 joules per mole Kelvin. What's T?
98.
It's the Kelvin temperature, right? Okay, what's F?
It's Faraday's constant.
65.
96.5.
96.
Okay? So if we do this at a constant temp, say 25 degrees Celsius, okay? Which is 298 Kelvin, right? Aren't these three things constants?
Yeah.
Yeah.
Oh, so I have a constant times a constant divided by a constant.
So it's always the same.
Let's
number.
find a constant.
There you go.
Good.
So let's take RT divided by F and find out what that would be. So 8.31 joules per mole Kelvin times 298 Kelvin divided by 96.5 coulombs per mole.
0.0257.
I have a question.
So RT all over F is 0.0257. What's your question?
How come they're rounding that 30 is constant? Because if
They
you
just
use
do.
the 485, wouldn't that be like a
It'll
significant
be
difference?
different, yes, it's just the way it's done in some books.
But if you use the 485, is that okay?
You're gonna get a constant here, so don't worry about it.
Yeah, why
Doesn't
does it
matter.
matter?
It's not gonna matter. Because the n can change, can't it?
Yes.
That's why we left the n out. Now, just wait, I'm not done playing yet. Okay? Now, in this equation, okay, we have the natural log of q, correct?
Yes.
Okay. For some strange reason, they want to get rid of the natural log of q and change it to the log of q. Okay? Because if you look on your AP Chem equation sheet, what's there?
Negative NF delta E.
You find, we're looking under electrochemistry. Let's see.
Log of A. Log of K. Log of Q.
They have, they have it both ways.
I don't know where it's at.
It's on the very last page, under oxidation reduction.
Oh, gotcha.
They have it two ways. They have an RT natural log Q, okay, which is actually how we have it right now.
Why does it say?
And then they have it as 0.05 times the log of Q. Okay, now, that's why I needed to show this, because someone's going to ask that later on. There's a mathematical relationship between the log of Q and the natural log of Q. Okay, great, here it is. Okay, this would be Q. Okay, and so don't write this, just follow for a second. Okay, unless you really, really want this.
No.
But the relationship between the natural log and the log is this. Really?
Really?
So much fun.
We're speedy today.
Get out of here.
No more.
I was just having fun.
No.
You're just gonna get But it is nice when the equations get simpler and simpler.
Yeah.